Ugh. Hopefully it's live. Let's see if I'm live. Checking. View my channel. Oh, it is live. Hopefully it's live. Alright, let's connect co-create. It's, why does it... Oh, there's a control panel? That's weird. Alright, today we are going to prove essentially Maschke's theorem. And we're going to do representations of compact Lie groups are semi-simple. And we're going to do... what else? I guess talking about group objects or vector space objects in various places and things. I think it'll be fun. But I want to get... Do you guys want to see chat? I think seeing chat's fun. Let's see if I can get chat in here too. Co-create. Let's switch scenes. Alright, we're getting there. I gotta... Oh, when I click away? Oh no, it disappears? Okay, that's not good. I have to pop out chat. Alright, better. Here we go. I gotta Google what Maschke's theorem is, just so that I know I'm getting the right thing. Why is Mac being annoying about this? Alright. Hey, what's going on? Also, Chris didn't even get to your best diagrams. I was really impressed with your ticks, I'm not gonna lie. How you got them into the equations? That was... I thought, it was very impressive ticks work. But today we are doing... Yeah, also a classic, but I think a classic that's instructive of a few things. Wait, let me Google. Is this Maschke's theorem? What is Maschke's theorem? Maschke's theorem says theorem that agrees deconvolutions irreducible pieces. Yeah, so this does cover Maschke's theorem. Is not divided separate? Yes. Okay. So we're doing finite groups and compact Lie groups. Well, I guess finite groups are compact Lie groups. Are semi-simple. And I'm doing this off of memory, so a few times I might have to think for a second. But the general gist is good. What was your paper again? If you link it. Oh, you can't link it. You can't link stuff on YouTube chat. I could actually... I can open... Can I open his last stream and find it? Let's see. 6 minutes ago? Does the chat still open? Oh, no. Okay, it might be hard to find your paper then. But if you describe it, I can Google it, and we can find it. But anyway. Well, yeah. The central theorem, or like kind of the general idea, 255, okay. archive.org, slash. All of this. Oh, yeah. Okay. It just downloads it. Scheme modules. It sounds interesting. Did you guys come up with a new algebra structure here? That's interesting. Do you think... Is this something that also categorifies? Because I know the Jones polynomial comes from or doesn't come from, is downstream from Kovanov homology. Did you know that Jones is like a physicist? He figured out the Jones polynomial while doing like statistical mechanics. Just found some relations. Oh, is this how we define some of the algebra structure? Interesting. I'm getting distracted. So I feel like at some point, because I want this to be a somewhat usable video, but I also think it's fun to just look at stuff, I'm going to transition to just proving representations of compact Lie groups are categories of quantum groups. Ah, interesting. Yeah, I don't know how the quantum stuff relates to all this, but at some point I want to learn a bunch of, well, specifically quantum computing stuff. I actually do theoretical computer science, and there's interesting technical differences also between the quantum case and the classical case. One of the biggest, you could say, issues or things that you have to deal with is you can't copy data in a quantum setting, the no cloning theorem. And that's something you do all the time in the classical setting. You copy states pretty much constantly. And in a lot of interactive proof or like zero knowledge proof or these things, if you've heard of any of these, the way we prove these things is that you have a simulator that essentially copies a computer at a certain step and then simulates it if you give it one input versus another input. And you just can't do that with a quantum computer. You can't go both ways because of the no cloning theorem. You can't copy a quantum state. And so there's a technical issue that you have to get around. But it's interesting stuff. Let me just get... I might need the power of... the almighty power of writing on an iPad to apparently the direction Microsoft was going with their topological quantum computing. This scheme theory is the right language to talk about things. Yeah, I don't know what's up with the topological quantum computers. I don't even know what that refers to. I mean, the funny thing is, like, because I come from like theory complexity world, in theory complexity world sort of treats quantum computers like they just exist and they're fine, in a little bit. And like a very prolific guy who's done a lot of public facing, just like math and science communication, is Scott Aaronson. And Scott Aaronson also does a ton in quantum complexity theory. And the tagline he talks about is that he studies what we can't do with computers we don't have. Because the problem that quantum computers face centrally to be viable is like, I guess, error correction. That, it's just reliability of the quantum gates, and so that noise doesn't kind of collapse a state. And that's really difficult. And that's, also a problem in regular computers, but that problem is so solved with regular computers that we don't even think about it. But because we're kind of coming from regular computer models, at least from the complexity theoretic standpoint, our models don't think about error correction as much. I mean, you might talk about error correcting codes and things like this if you're doing communication. But if you describe Shor's algorithm, you're not like optimizing it so that you have redundancy so that you don't have a bunch of errors. Like, there's a very good lecture I watched in the beginning of a quantum computing course that talked about how, what's the problem with making a pool-based computer? Because you can make all the gates you need to make a computer with like pool cues, and you can like hit a ball, and if there's some balls there, it'll go in different directions, and you can make this mechanical computer. And what's the problem with this? And there's a bunch of computer science students, and they all think in the things that we typically think about. They think, oh, it's too slow, or oh, it's how would you handle memory? It's too big. But the real central problem is error handling. Is that if you hit and the ball doesn't go perfectly straight and the bounces aren't perfectly aligned, you'll just get a mess. You'll get a bunch of balls in this table with a bunch of walls that won't do what you want it to do. We take the reliability of computation very much so for granted. And that's something that maybe we should not do. Well, no, it's something we can't do with quantum computing, and that's making scale difficult. But it's funny I'm talking about all this because the problems of making this stuff reliable is also not what I work on. And I also don't work on quantum complexity theory. So I'm 2 layers out of my expertise, but it's stuff I want to learn more about. And I might do quantum related cryptography or complexity theory down the line because I'm really interested in that stuff. And I kind of think there's two problems. It's famously known that quantum computers solve RSA because it can do factoring. I kind of think, and I think a lot of people think, that quantum computers also solve lattice-based problems, that if we're a little more clever, we can figure out how to break lattice cryptography, which is what our entire post-quantum cryptography is based on right now. But we just haven't figured it out. It'll just take someone to figure it out. But I think it's more likely than not that quantum computers, there's a polynomial time quantum algorithm that can break lattice cryptography. But we don't know it yet. So it's it's safe until you know the solution. But yeah. Also, I don't know. I think you're the only person here, and if you want, we can talk about something different because I got a lot of things. There's a lot of things I like discussing about. I do a bunch of random math, computer science stuff. I could talk about an information theory thing that I was thinking about. I could do that because I might guess that more representation theory. I was planning this morning to record this video just going over this proof, and the way the proof would work is that if I have if I have a representation, I just want to show that these functors are the same. And that would show, oh wait, that's not. Those functors definitely are the same. No, these functors are the same. And then I would use the exactness because the left one's left exact, the right one's right exact. In the case of compact Lie groups and finite groups where the characteristic doesn't divide, these functors are equivalent. And then exactness shows that if I have a short exact sequence, something like this, we'll call it row U, right arrow, row, right arrow. We'll call this row S. I need better names. Right arrow 1. Oh, these should be zeros. 0. We're not multiplicative. Right. I was thinking too much of those groups in cryptography. If I have something like this, you can do a clever trick using the exactness to show that this short exact sequence will split. You can show that you can essentially, that the surjectivity on the Hom sets also holds, and the G-fixed of the Hom sets will give you the G maps, which I'll try to show all this because I also don't 100% remember, but I bet I can figure it out. And then you could show this short exact sequence splits. So I'm happy to have that be what stream is today, but I'm also happy to talk about other things. Like one thing that might be a little more different, if this is something you're already familiar with or don't want to hear about, is I was also working on a proof that the F divergence of, what is it? X comma Y. I guess I should write this different. P x comma y and px py cal d. Yeah, it doesn't have my math cal d. We're gonna say pw. That this is minimized by pw equals py. You're kind of down for anything. Okay. Well, I think more of my audience would be more interested in this rather than this random information theory thing. But I'll probably do a video on this later. Because this statement, oh, I don't want to give stuff away. Well, I don't think it gives stuff away. I needed this statement for research thing I was doing, and it does work. It does have to use a little more analysis than perhaps I'm as comfortable with, but it's easy enough. Like, you want to show that a certain derivative is 0, which is easy enough. Okay, you show a derivative is 0, but it's a derivative between an infinite dimensional space and a finite dimensional space, which is like, okay. Well, between an infinite dimensional space and R. And showing that 0, you can do all the directional derivatives in that space. And so it does work out, but it could be, you could say, better handled in certain ways. Oh no! Oh no! I just dropped my knockoff Apple Pencil. Now I have to go get it. Let me see. It fell through the cracks. Oh, come on. Drop mine. And see, I'm not extremely well set up. Let's move this back a little. That's it. I don't know if you can hear the guitar. Okay, we're getting there. Perfect production quality. Nothing's wrong. Alright, let's do this proof. I have to hook up my laptop. I'm not as well set up as yeah, it was. I'm in bed right now. It just fell through the cracks. And I'm like, oh god damn it. But now I got a 1024. I'm actually just gonna put this in chat. I usually hide the links so that people don't grief it, but there's not enough people here, so I can literally open up the screen on my iPad and then get the link so that I can write on the iPad from the stream. Cheers. We're getting there. Okay, opens it, go to live. Go to the link. Get the link so that I can write on the iPad from the stream. And here we go. Am I algebra? Oh, is that you? That's funny. Well, if I make a mistake, you can point it out. But I've heard it's confusing because it's out of sync. How have I lost the Apple Pencil again? This is the most difficult stream I've ever had. What the? Oh, there it is. It's literally on the laptop. All right, let's do this. Now that let me just test that I can write on the iPad. Let's see. Let's turn this on. Write something. All right, that's good enough. And now we're going to just prove this thing. Oh, I don't want it to be. Let's delete these. Yeah, that's what Arad told me, that the delay was difficult. But Gonna delete this, delete this. I'm basically setting it up because I might essentially cut this later, so that I have this as a video where it's just this part. All right, today we are going to do Maschke's theorem, which says, among other things, that you can that any representation of a finite group, well, any finite dimensional representation is somewhat important, of a finite group splits into a sum of irreducible representations if the characteristic of your base field, so char k, doesn't have characteristic. If P does not divide the size of the group, where P is the characteristic, of the base field you are working over. And you might need, I think of it as big boy rank nullity theorem. That's interesting. I mean, rank nullity is just when things split cleanly. So I guess this is an example where things split cleanly. I think of all of homological algebra as big boy rank nullity theorem. But most of that's about rank nullity somewhat failing. And we're also going to prove this, a similar theorem that we might need to work over an algebraically closed field to always have a subrepresentation. But maybe I'll find that out while I'm proving this. And then we're going to prove finite dimensional representations of Lie groups also split into irreducible representations. And we're going to prove these at the same time because the proofs of these are morally similar, and it's going to use a certain fact that in both of these cases, there are two functors. Say I have rho as a G representation. It's a G representation, over a field K. We don't know anything about rho, G, or K, but there is a functor where rho maps to the fixed points. And so this is specifically rho G is equal to all those vectors in rho, v in rho, such that GV equals V for all G and G. Maybe I should put that in, for all G and G. So there are the fixed points of your representation. You have a G action and you have fixed points. And these are called the invariants and are rather important. Something that you should probably also know about, but is talked about much less, is there is sort of a dual to invariants called co-invariants. And the co-invariants we do similarly, but we do a subscript. We say this is equal to, and then we actually have to take a quotient. So we can't just describe it. So if we have the underlying vector space as V, we take the quotient by a vector space W, where W is the subspace of V, that is given by precisely these vectors, GV minus V, for G in G and V in V. So if V is your underlying vector space, like you have your group G, big ol' G, which is finite or compact, and it's acting on vector space V, then we quotient out and we sort of kind of kill all of this G action in a sense. In this one, we're finding the subgroup where everything's fixed. And in this case, we're killing all the vectors, we're setting them equal to 0. Well, we're not setting them equal to 0, we're forcing them to be fixed. And so this is coinvariance. And the thing that we'll find is that in both these cases, so in both the cases here and the cases here, we'll have that these two functors are one and the same. Or they're isomorphic. So maybe I should write symmetric here. They're naturally isomorphic as functors. This is the big key statement. And once we know that they're the same, using this statement, we can prove both of these theorems, because the proof is similar in both ways. And in fact, I'm just going to sort of talk about how you can do this sort of abstract proof, because, you know, what we're working with here with compact Lie groups is somewhat different than working with finite Lie groups. So how do you do a proof that's exactly the same? And the answer is that you can work in a very general setting. Oftentimes we're kind of loose about this, but you can make it well defined. So next step is, how do we prove two theorems at once when their domains are different? Because frankly, a finite group acting on maybe a finite dimensional vector space over FP bar is pretty different than like a Lie group working over a complex vector space. I'll have to think about this, but I think we might need algebraic closure, but maybe we don't. We just need it for... Actually, I think maybe we don't. Well, while proving it, I'll probably find out. And so, how do we do this? Well, we work in a very general setting. Representations in general, we have a group acting on a vector space. And we're going to change to a group object acting on a vector space object. So what does that mean? Well, if I have a group, you can define a group with a few things. You know, you have a set G, you have multiplication, so you have something that's like a map like this, where you have some properties, G times G goes to G, and you have like associativity, and so you have like two different maps, G times G, G times G, right arrow, G. And we say these two maps are equal, G times G times G, right arrow G. Oh, and you might be asking, what are these two maps? Well, these maps, the first map is basically A times B times C, and the second map is A times B times C. And if these are equal, if these functions are equal, then that's exactly stating that these things are associative. And that's cool and all. And you have similar properties that you can express. You have a map from G to G given by inversion, because you have inverses. And you have all of these things, and they have these properties that you can express as these set maps. And when you change it to a group object, all you do is you take all the same axioms of a group, and you say now all of these elements, the G's, they're not just sets, maybe they are manifolds. That they are finite dimensional manifolds, or infinite dimensional manifolds. And that's precisely the definition of a Lie group. You could define a Lie group. A Lie group is defined to be a group object in the category of manifolds. So what are you doing? You're just taking your regular axioms of groups, and you're enforcing that every single map you care about is a smooth differentiable map. And so, you know, if I have something like, here's a simple Lie group, it's just the real numbers. It's not a compact one, and so we're not going to math BBR. What does it not like about that? It's not a smooth it's not a compact Lie group, so it's not going to show up in this theorem. But this map, given by addition, is differentiable in both variables. In fact, the derivative is 1 in both variables. And so it's definitely smooth. It's not too much going on. But anyway. Live chat. All right. So we take R times R, maps to R. And we have a Lie group. It's given by these. And for Maschke's theorem, it's a little easier because it's a group object in set. So groups are group objects in set. And we can do the same exact story with vector spaces. Vector spaces, they have addition. So we define a vector space object with addition. They also have some notion of scalar multiplication. K times V, right arrow V. And you have all these properties. And to transition from something being a regular vector space to a vector space over object in a manifold, you enforce that all these vector spaces are manifold and all of these maps are smooth maps of manifolds. In our Maschke's theorem example, we are still working with vector space objects over sets, which are just vector spaces. But here, what does this do? Well, this essentially just enforces that our representations also have to be continuous and smooth. And so it makes things easier. But now that we have this really general framework, we can prove something that, say, our meta theorem, here's the meta theorem, that proves both of them. If I have a group object, G, in, some category C, and I have a vector space object, and I have a vector space, let's go down, object in V in C, and I have an action, again, in C, so like our action will be expressed like this, where all of these morphisms happen in the category C. That gives us a representation in C. If the functor, because now we can go from functors of G representations in C over some field K, so if the functor rho to the G is naturally isomorphic to rho to the G, then representations split into irreducible representations. Now, I've been kind of loose here. There's, more things I would have to specify. I'd have to specify that the field is an object in C, and I'd have to specify that that there's a notion of finite dimensionality of these vector spaces for it to split completely. Because what I'm going to show is that if I have a sub-representation, then you can split it off. And that's useful, but if you don't have some finite dimensionality condition, you could keep splitting forever, and you would never get down to your full direct sum in a lot of cases. And so, is there a nice way to express finite dimensionality? Yes, there is. Okay. So, finite dimensionality one is exactly when we have a surjective morphism like this. Epimorphism in C. K to N to V. And so, the meta theorem is that if we have this kind of setup where the fixed points, the sort of trivial representation, the invariance and the co-invariance are isomorphic, then things split completely. And that allows us to prove both of these theorems at the same time after we've shown that rho to the g is isomorphic to rho underscore g. And it's like, okay, well, there's sort of two directions we can go. So this would be over the category of sets. This would be over the category of smooth manifolds. Should we start with the meta theorem, or should we start by proving in both cases that this is the case? I'm actually going to start with the meta theorem because it's interesting. Actually, no, let's show this. It's getting ahead of ourselves, but I'm going to make a full plan. So here's the plan. One, show for both cases that this holds. G. Two, show that this means that the functor rho to the g is an exact functor. Three, show that the invariance of Hom k, you know, rho 1, rho 2. Backslash Hom. Oh, we don't have Hom? Unfortunate. That this is exactly isomorphic to what we want, which is the G Hom. Text Hom. So G of rho 1, comma, rho 2. And once we show this, prove the meta theorem, and thus prove Maschke's theorem, and prove that for finite dimensional representations of Lie groups also split into irreducible representations. Oh shit, Nikolai, how are you doing? You interested in learning some representation theory, basic representation theory? Let's start with Maschke's theorem case. So we'll zoom in a little bit. Actually, let's get another page. All right. Maschke's theorem case. So G is finite and not divisible by the characteristic of K, which is our base field. So what do we want to show? We want to show invariants are isomorphic to co-invariants. One question is, how the hell would we show that? How would we go about doing that? How do we get a map between these two things? And the map is actually the easiest part. If we have the invariants, this is just a sub-vector space of the vector space which is our representation. And then you'll notice that this surjects onto the co-invariants. So Lie groups up, I have 0 times. Well, Nikolai, at least in this video, maybe you can learn a little bit. Hopefully it's helpful. And so we have this map where we just take a vector that is fixed, and we end up with a vector in the G invariance. And so this gives us our isomorphism, but we have to show that it's an isomorphism. And one way to do that is to give an inverse. So let's find an inverse, and the inverse is called symmetrization. And so we want to find our inverse map, rho G to rho G. Oh. And our inverse is going to be given by symmetrization. So the idea is here, what do we have here? We have a bunch of vectors which are fixed. And here we also have vectors which are fixed, but they may have started out not being fixed. But we can do something clever. We can give a map from here to here. We're going to do this. And what's special about it is it's going to be the identity on. I should label this X, and we're going to call this sim for symmetrization. Maybe sim G. And it's going to do two things. One, it's going to fix the fixed vectors. So the subspace of fixed vectors of our representation will be sent by the identity to rho g. And it's going to send all the other ones to fixed vectors. Like this is going to be a G map, essentially. Actually, is it going to be a G map? No, it's not necessarily going to be a G map. Ignore that. So what is this map? Well, it's very simple. It sends a vector to this frac 1 over G, sum of G and G of GV. Boom. Symmetrization. A while ago, I was working on this tensor rank problems. And when I was working on tensor rank problems, I remember using symmetrization to get symmetric tensors and tried to show lower bounds on tensor rank using symmetrization, because I noticed all the bounds I was going for were already symmetric. And it had mixed success. It helped a little bit. But it wasn't... Honestly, I could have desired more. So what happens? What the hell is this thing doing? Well, let's say W was a vector in rho G. So something that was already fixed. That means GW equals W for all G. Okay, so then what happens? Then if we take sim of W, this will be equal to, we do our frac 1 over absolute value of G. And then we do the sum underscore G of GV of GW. Well, GW is equal to W for all G because we assume that W was fixed. So we just get W. And so then we get exactly the frac 1 over G times G times W, which equals W. So the symmetrization of an already fixed vector gives you the vector back. Okay, cool, I guess, you know. You also have to ask a question like, who cares? Then the other thing to note is, you know, does this thing actually work? Does this land in the fixed vectors? Because a priori, this is just a map from V to V. You know, what happens to everything else? Well, suppose I take an arbitrary V and I multiply it by sim G of V. What do I get? Well, I'm going to copy this because I don't want to keep writing it. I get this where, maybe I should write H here. So H times sim G of V. I get HGV. Well, H, left multiplication by H is just a bijection on G. Like, if I sum through this over all of the elements of the group, this will exactly sum over all of the translates by the group exactly once again. So this is equal to sim V, sim of V all over again. And so this shows that for an arbitrary translate, I'm going to make this smaller. For an arbitrary translate, sim V does fix it, which makes this a valid map. Now the last thing we want to show is what does it do on W, on the W subvector space. If we go all the way back here, the coinvariants were defined by quotienting out by this vector space, W. And this vector space W is spanned by these guys. Oh, I shouldn't say it's equal to this. It's spanned by this. Let me just fix that. It's the span of these guys. Span of these guys. What does it do on W? Well, if we say W is in W, and then we apply sim G of W, well, let's assume that W is one of the span vectors, because we're going to show that it's 0, and so W is a sum of span vectors, so it will be equal to 0 if we show on this spanning set it's equal to 0. So this is equal to sim GV minus V. Okay. Well, this is linear. So this is equal to sim underscore G of GV minus sim underscore G of V. Cool. What does that give us? Well, this, if we go back, what is sim underscore G of GV? Well, using the same translation argument that was given right here, well, it actually does the right translations. So it's a very similar translation argument, but sim underscore G of GV is equal to sim underscore G of V. And this is equal to sim G of V. And so we conclude that this is equal to 0. So what do we have altogether? We have this special map, the symmetrization map, that fixes rho underscore G. So if we precompose it with rho, it's the identity on rho G, and it's 0 on W, which is what we quotient out by to get the coinvariance. And if we use the universal property of the coinvariance of a quotient of vector spaces or of groups or whatever, the third isomorphism theorem, this exactly tells us that this turns into a map from rho G to rho G, because it's a map from V to rho G that's 0 on W. And that's exactly what we need to get a quotient. Okay, so we said a bunch of things. The question is this an inverse? Well, it's an inverse on one side we've shown already. Because it's the identity on rho G, we already have that this composition, right arrow V, right arrow rho G, right arrow rho to the G. Okay, I might have to draw something. So our original definition of symmetrization is a map from here to here. But because of the universal property and it being 0 on W, we get an induced map in purple from here to here, such that all these compositions together. And because we're terrible, terrible mathematicians who abuse notation, we're going to call these both SimG. We're going to use the same exact notation for both of these maps. SimG of V, and also SimG of V. Because that's just how we do things. But we know this is the identity on rho G, so that already shows that if this is our first, it's a bit less obvious to me, but I think this may work with monoids and monoid reps. I don't see any uses of inverses anywhere. Let me think. Rho G, it fails here, I believe, because you need a bijection. This is where it fails on monoids, because you need exactly this property to hold. If it was you need this to be a bijection, which means you have inverses. So it doesn't work for semigroups either, because if you do a semigroup and I do a translate, the sum might be different. You need a bijection for it to be fixed. So it does need groups beyond just monoids. All right. Well, that's a good point. I had never thought about monoids, so it's good to know that you do need the full group axioms, specifically, so that this relation holds. All right. Going back to this. So we've already shown that this composition is the identity. The other thing is to show that the other composition, if we go first rho underscore G, and then we go all the way back to rho G underscore G, that we get the identity map. So how do we do that? Well, let's just follow and see what happens. If I have an element v in row G, which is some quotient class of my original vector space, you go here, and then here, and then here. I kind of want to use a dimension argument because that sounds like it would be easier. But maybe there's a clean composition argument because I've shown that one of the sides is inverse. And if I show they have the same dimension, then everything's good too. But maybe that's not the best way to go. Oh, can I go through it twice? If I say this is the identity, and then I go all the way back and this is the identity. No, that's the same thing as, that would only work if the dimensions matched. All right, now thinking time. Oh, I didn't plan to think. Let's see how we can show that rho G. Well, let's just follow it. Let's just see what happens. So we have a vector v, which can be a class of any vector in our original vector space, big V. And so it can be v, you can say plus a bunch of stuff, and then we send it, v maps to what? To, 1 over g, sum underscore g of gv. Then, so we lift here, we take a symmetrization, which gives us a fixed vector here, and then we go here again, and then we go here again. Okay. Oh, okay. I see what we have to do. So saying that this is the identity on row underscore G is exactly saying that if I lift to a vector here, and then I go here, and then I go here, and then I go back, the difference between these two has to be contained in W. It has to be made up of a span of these vectors. Because if the difference is in W, it gets zeroed out when we post-compose here, and they were equal. So all we have to show is that precisely this is in W. And how do we do that? Well, we do a few tricks. We see that V is also equal to G over G, V. Now we have a common denominator. And with a common denominator, we can sneaky snake, we can slip this into the sum here. And what do we get when we slip this into the sum here? We get exactly frac 1 over G of sum G of V minus GV. And all of these elements are precisely what we want. All these guys, oh, I have the wrong tool. All these guys are just negative ones of span vectors from W. Remember, W is the span of these guys. So if you multiply them by negative 1, you get a bunch of these guys. So it means the difference between V and its symmetrization is in W, which means they're equal when you quotient out by W. So this was a lot of words, and I'm sorry that my board work is terrible. Maybe that's what I should really work on. But this is how you show that precisely as we want, that rho G is isomorphic to rho underscore G. And this will be the key ingredient to proving Maschke's theorem. The only thing I did not touch on is why did I need G, the absolute value of G, to not be divisible by the characteristic? Well, I need to be able to divide by the size of the group so that fixed vectors map to fixed vectors. And I can't do this in characteristic P if P divides G because it's like dividing by 0. And so that's exactly why you need this condition, the non-divisibility, is to be able to do division. All right, let's do the Lie group case, The Lie group case is almost exactly the same. So I'm going to go through it a lot quicker. I'm just going to be honest. The Lie group case on page 3. So if G is a compact Lie group, then rho G, simic, rho G. Well, we have the same story. We have these maps, exactly as before. We have the inclusion into the vector space, and we have the quotient by exactly the same thing, coinvariance, by GV minus V. Cool. So, what is the map? Rho G to rho to G. What is it? Well, it's symmetrization again. If G is compact, we can integrate over it. And that is the key difference. And because G is compact, we can also choose a volume form such that it has volume 1, so we don't have to divide by the size of the group. And so we're going to define a similar map, sim G, that goes from V to rho to the G. And what's it going to do? Sim G of V is going to be equal to now instead the integral over G and G of G and G of GV. And because we have our nice smoothness things, by the same arguments, this will also be fixed by translations. I'll have H sim G of V will be equal to sim G of V. And it's a similar thing where here we get the H commutes into the sum. Here the H commutes into the integral. It's really almost exactly, it is the same story. You know, the two pictures, these are the same picture. All right, well, what's the next thing we get? This already shows, as explained by the same argument from before, this already shows that this map, sim, that goes back to rho G, the invariance, will compose to be the identity. So this already gives one layer of composition. Okay, what about the other thing? What about descending to this? Well, again, we just need to check V minus sim underscore GV. Actually, is that what we need to check? No, that's not what we need to check. We need to check sim underscore G, GV minus V. We want this to be equal to 0. Well, again, it's going to be the exact same thing. You can really just replace the integral sign with sums, or the sum signs with integrals, and do the exact same argument. So you do the same argument, you say the integral underscore G of, we have to make this H again because I can't think of more letters. Well, what is this? I mean, this is a linear map, so we already know it's linear. Well, we have GHV on one side minus the integral underscore G of GV on the other side. Well, this, and this is using the group property, is a smooth bijection on G. So it's measure preserving, and so the integral we get here is equal to the integral we get here, so we get 0, which means that our sim map descends to being a map from rho underscore G back to the fixed invariance. And so we can define our sim G at the level here. Now, because I'm going to skip fixed, that fixes rho G, and I'm going to do the exact same argument that I did to end this one, that if I take a V and V, then I want to show that sim underscore GV minus V is in W. And this is going to show that when we compose, when we go from sim G to here to here to here, that we'll get an equality. Because if we do this, we might not get an equality in V, but once we quotient, i.e. once we say all the vectors in W are 0, we'll get an equality. So what do we get? Well, it's the same story. Wait, is this what I want? I want sim g minus v. Yes, this is what I want. Because I'll get that this is equal to int underscore g of gv minus int underscore g of idv. Oh, I'll say iv for the identity. Well, this is equal to the integral underscore g of gv minus v. But all these gv minus v vectors are 0. Once we quotient, well, they're in W. And so the integral of this, because, W is a closed subspace, we're in finite dimensions, so it's always closed, will lie in W, the integral of all of these pieces. And so that says that the quotient will be 0, which means that this thing is equal to this thing once we do our, triple composition and go from rho underscore g back to rho upper g. All right, so that's sort of a very quick saying the same things again. Cool. This is going to be a long stream, I'm realizing. Should I do this in multiple parts? How are you guys feeling? Who's here? Is anyone here, or is it just me? Maybe it's just me. Let's see. Well, let's look at the plan again. The plan. Show that this means, yeah, exactness. Well, there's two more steps. Exactness of rho g. And then exactness implies splitting of short exact sequences. So these are the two things we have to show, and then once we can split our short exact sequences as we want to, this will show that I think we don't need algebraic closure because I'm just like doing the proof in my head. And you still have irreps over R, and so I don't think we need algebraically closed fields. But I think I've been going on for a while. Let me see. AMA, basic representation theory. How long have I been going? I've been going for an hour. So I think I'm just going to come back to it. We're going to do a part 2. And the part 2, we're just going to prove this. That this isomorphism implies this functor is exact, and the exactness shows splitting of short exact sequences. And once we do that, we've proved both of these theorems. So this is a part 1. But this has been fun. Thanks for everybody who stopped by to show this. I'll relabel this stream. And I'm probably going to record a set theory video today. So it might be a little bit before I get to part 2. But it's fun to go over this stuff. And maybe it should be an exercise. How do you show that if these two functors are isomorphic, that they're exact? If you're not so comfortable with functors, try to do this stuff, but show that that these are functorial. Because I just showed they're isomorphic. I didn't show they're functorial. But that's just sort of a bunch of annoying, whatever, busy work, in my opinion. Whatever. But anyway, see you guys around. It's been fun. All right.